Picture the universe as a grand cosmic puzzle, where most of its pieces remain hidden in plain sight. Dark matter, one of the most elusive and enigmatic substances in existence, makes up roughly 85% of all matter in the cosmos, yet it refuses to reveal itself directly. We can't see it, touch it, or even detect it with traditional instruments, but its gravitational grip holds galaxies together, shaping the very fabric of space itself. And surrounding those galaxies like invisible cloaks, mysterious structures called cosmic dark matter halos, vast, ghostly envelopes that defy our understanding and challenge everything we think we know about the universe. What exactly are these halos, and why do they leave even the brightest minds in astrophysics scratching their heads? Imagine a spider web, its delicate threads stretching far beyond the spider at its center. Dark matter halos are like that, silent, sprawling, and impossibly massive, extending far beyond the visible edges of galaxies. They're the unseen architects of cosmic structure, dictating how galaxies form, spin, and collide. But here's the catch: the more we learn about them, the more questions they seem to raise. Their behavior defies predictions, their distribution baffles simulations, and their very existence hints at physics beyond our current theories. That's where the real mystery begins. Over the next 25 segments, we'll journey deep into the heart of these cosmic enigmas, unraveling why dark matter halos shouldn't exist according to some models, how they might hold clues to parallel universes, and what their strange, uneven shapes could mean for the fate of our own galaxy. From ghostly particles that pass through you like you're not even there, to colossal halos bending the light of distant stars, this is a story of scientific detective work on the grandest scale. So buckle up. By the end, you'll never look at the night sky or the invisible forces shaping it the same way again. If we can't see dark matter, how do we even know it's there? The answer lies in the cosmic equivalent of footprints in the snow, not from the thing itself, but from the unmistakable mark it leaves behind. Take gravitational lensing, one of the most mind-bending tools in an astronomer's toolkit. Here's how it works. Imagine space as a trampoline and a massive object like a galaxy cluster as a bowling ball placed in the center. The weight of that galaxy warps the fabric of space-time, bending light from distant stars as it passes by, just like how a bowling ball would make a marble roll in a curve around it. But when scientists measure these cosmic curves, they often find the bending is far more extreme than the visible matter alone could explain. That extra warp. It's the fingerprint of an invisible giant, the dark matter halo, flexing its gravitational muscle. This effect isn't just theoretical. Some of the most striking evidence comes from places like the Bullet Cluster, where two galaxies collided in a cosmic wreck. The visible gas stalled like two clouds smashing together, while the dark matter, unaffected by friction, kept right on going. By mapping the distorted light from background galaxies, researchers could essentially trace the outline of the dark matter halos, striding ahead of the visible wreckage like ghostly silhouettes. It's as if we're seeing the shadow of something colossal, cast not by light but by gravity itself. Yet for all its power, dark matter's invisibility isn't just about lacking brightness. Unlike stars or gas, it doesn't absorb, reflect, or emit any form of electromagnetic radiation. No radio waves, no X-rays, nothing. It's not just dark, it's utterly transparent, passing through ordinary matter like a breeze through a screen door. That's why our telescopes, no matter how advanced, draw a blank, but gravity doesn't lie. The way galaxies rotate faster than they should, the way light bends around empty patches of space, even the way the universe clumps together on the largest scales, all of it points to an unseen scaffold holding everything up. So what's next? Scientists are now deploying even stranger methods to chase these phantoms. Some hunt for ultra-rare interactions deep underground, where dark matter particles might bump into atoms in vats of liquid xenon. Others scan the skies for anomalies in gamma rays, the last possible whisper of dark matter annihilating itself. Every experiment narrows the possibilities, yet the halos remain stubbornly elusive. One thing's clear: the more we learn about these invisible giants, the more they rewrite the rules of the cosmos. Even with dark matter halos solving so many cosmic puzzles, there's another layer to this galactic mystery, one that involves the very stuff we're made of. Ordinary matter, the atoms in your body, the stars in the sky, everything we can see and touch, is known as baryonic matter. And here's the kicker: when scientists tally up all the baryons in galaxies, the numbers don't add up. There's a glaring shortfall, a cosmic accounting error where up to half of the expected ordinary matter seems to have vanished without a trace. This is the missing baryon problem, and it's forcing us to rethink where, and in what form, the building blocks of the universe are hiding. So where did all these baryons go? One clue lies in the vast, faint webs of hot gas stretching between galaxies, too diffused to glow brightly but thick enough to hold a significant chunk of the universe's missing matter. Picture a sponge soaked in water. The galaxies are the solid bits, but the real volume is in the tiny, nearly invisible pockets of liquid between them. Similarly, these intergalactic filaments, heated to millions of degrees, emit faint X-rays that only the most sensitive telescopes can detect. Yet even when we account for this, there's still a gap, and that's where dark matter halos come in. These halos don't just contain dark matter, they also act as gravitational traps, slurping up stray baryons like cosmic nets. Some theorists suggest that halos may harbor enormous reservoirs of cold, dim gas or even exotic particles we've yet to identify. Others propose that the missing baryons could be hiding in plain sight, woven into the fabric of the halos themselves, too spread out or too faint for our current instruments to spot. It's as if the universe is playing a shell game, and we're still learning where to look. The implications are staggering. If we can't even account for all the ordinary matter, how confident can we be about the rules governing the cosmos? This discrepancy challenges our models of galaxy formation, suggesting that the way matter clumps and flows might be far more complex than we imagined. And it raises a haunting question. If dark matter halos are hoarding baryons, what other secrets might they be keeping? The hunt for these missing pieces isn't just about balancing equations, it's about uncovering the hidden architecture of reality itself. If dark matter halos are the invisible scaffolding of the universe, why don't they look like the galaxies they hold together? You'd expect them to mirror the elegant spirals or flattened disks we see in the night sky, but nature loves to defy expectations. Instead of taking on the shape of a frisbee, these halos resemble something closer to a lopsided beach ball, more spherical than flat, with some even stretching into ovals or asymmetrical blobs. This mismatch isn't just a visual oddity, it's a clue to the fundamental differences between how dark matter and ordinary matter behave. Think of it like pouring two liquids into the same glass. Ordinary matter, gas, stars, planets, clumps together, cools down, and eventually settles into a spinning disk due to friction and collisions. But dark matter, it's like a ghostly syrup that never thickens, without any way to lose energy through collisions or radiation. Its particles just keep orbiting in vast, messy clouds, tracing overlapping paths that blur into a roundish haze. Simulations have predicted this for decades, painting halos as near-perfect spheres in isolation. Yet when astronomers compare these models to real-world observations, things get weird. Some halos appear flatter than they should be, while others show strange, lumpy distortions as if something or someone has been tugging at them. The plot thickens when you consider collisions. When two galaxies merge, their dark matter halos don't smash together like the stars and gas. Instead, they pass through each other like phantoms, barely slowing down. This creates chaotic gravitational tides, stretching the halos into elongated shapes or leaving behind faint, streaky trails. The most striking examples come from galaxy clusters where halos seem to stretch like taffy, their forms warped by the pull of neighboring giants. It's as if space itself is a funhouse mirror, bending these invisible structures into shapes no simulator saw coming. So why does this matter? Because the true shape of a halo isn't just cosmetic, it holds the key to understanding dark matter's nature. If halos are fluffier than predicted, it could mean dark matter particles interact with each other in ways we haven't accounted for, perhaps through some unknown force. If they're more jagged, it might hint at hidden turbulence in the early universe, like echoes from a cosmic battle we can't yet see. Every distortion, every unexpected curve, is a whisper from the dark side of reality, urging us to rethink what we know about the glue that holds the cosmos together. One of the most puzzling mismatches between theory and observation lies at the very heart of galaxies where dark matter should pile up like snowdrifts, yet instead it seems to vanish into ghostly hollows. This is the cusp-core problem, a mystery so persistent it's shaken astrophysics to its foundations. According to decades of simulations, dark matter halos should be densest at their centers, forming sharp cusps where gravity pulls particles into a steep, mountain-like peak. But when astronomers measure the actual distribution of mass in galaxies, especially small, faint dwarf galaxies, they find something startling. The centers are more like gentle hills than jagged cliff, smooth cores where dark matter appears oddly diluted, as if someone scooped out the middle. So why does reality refuse to match the math? One camp argues our simulations are missing a critical ingredient: ordinary matter. Stars and gas don't just sit idly in halos, they explode, collide, and churn like a cosmic blender. Some theorists suggest that when supernovae erupt, their shockwaves could push dark matter outward, carving out those fluffy cores over billions of years. Picture a spoon stirring honey. The swirls and eddies might redistribute the syrup, leaving the center less dense than expected. Yet there's a catch. While this works for small galaxies, larger ones have enough gravity to resist such mixing, and yet some still show cores where cusps should be. The numbers don't add up. That's led others to question dark matter itself. Could the particles interact in ways we haven't imagined? Modified Newtonian dynamics, or MUND, proposes scrapping dark matter entirely, suggesting gravity behaves differently at galactic scales. But MUND struggles to explain phenomena like the bullet cluster, where dark matter's gravitational shadow is undeniable. A wilder idea: dark matter might be self-interacting, bouncing off itself like microscopic billiard balls, which would naturally smooth out those dense central cusps. It's a tantalizing fix, except no experiment has yet found evidence for such interactions. The stakes couldn't be higher. If dark matter isn't cold and collisionless as long assumed, entire chapters of cosmology might need rewriting. Alternatively, if baryonic physics is responsible, we're overlooking something fundamental about how galaxies evolve. Every dwarf galaxy with a core is a silent rebuke to our models, a cosmic wink urging us to look deeper. Solving this riddle isn't just about dark matter. It's about uncovering whether we've misread the universe's blueprint from the very beginning. Dark matter might be invisible, but it isn't all the same. Some of it could be downright frosty, while other varieties might zip through space at blistering speeds. This is the heart of the cold versus warm dark matter debate, a cosmic tug of war over how fast these elusive particles move and what that means for the universe's largest structures. Cold dark matter, the traditional favorite, is the slowpoke of the bunch. Picture molasses on a winter day, sluggish and heavy. These particles clump together easily, forming the dense, sprawling halos we see anchoring galaxies. But warm dark matter, that's the speedster, lighter and faster, leaving a subtler imprint on the cosmos. The difference might sound academic, but it's anything but. The temperature of dark matter doesn't just affect how halos form, it reshapes the entire cosmic web, determining where galaxies cluster and how they evolve. Take dwarf galaxies, for example. cold dark matter predicts they should be everywhere, peppering space like confetti. Yet we find far fewer than expected, a discrepancy that's puzzled astronomers for years. Warm dark matter offers a potential fix. Its faster particles would smooth out small-scale clumping, leaving fewer dwarfs in its wake. It's like comparing two painters, one using thick strokes to create detailed textures, the other with a lighter touch, leaving broader, softer patterns. But warm dark matter isn't without its own headaches. If it's too speedy, it might struggle to explain how the universe scaffolded itself so quickly after the Big Bang. The cosmic web we see today, with its intricate filaments and voids, might not have had time to form. Then there's the particle puzzle. Cold dark matter's leading candidate, WIMP, weakly interacting massive particles, are the strong, silent types, hefty enough to sculpt galaxies but elusive enough to evade detection. Actions, on the other hand, are the featherweights of the dark matter world, trillions of times lighter than electrons, yet possibly abundant enough to fill the cosmic gaps. Some experiments, like ADMCs, are hunting actions by tuning them like radio stations, hoping to catch their faint signals. Others, like the LUX Zeppelin detector, lie in wait for WIMP, buried deep underground to shield from cosmic noise. So far, neither has delivered a smoking gun, leaving the temperature debate wide open. What's fascinating is how this divide forces us to rethink the universe's adolescence. If dark matter is cold, the early cosmos was a grainy place with tiny clumps merging into galaxies. If it's warm, structure formed top-down with vast sheets fragmenting into smaller pieces. The answer could rewrite our understanding of cosmic evolution, not just how halos grew, but why the universe looks the way it does today. Until we pin down these phantoms, their temperature remains one of the most heated mysteries in physics. If dark matter halos are cosmic architects, then satellite galaxies should be their most obvious handiwork, small, obedient companions orbiting larger galaxies like fireflies around a lantern. But the universe has a way of defying even the most elegant blueprints. Enter the too big to fail problem, one of the most stubborn headaches in modern astrophysics. According to supercomputer simulations, the Milky Way's dark matter halo should host dozens of hefty satellite galaxies, each with enough mass to resist disintegration. Yet when we peer into our cosmic neighborhood, we find far fewer of these behemoths than predicted. It's as if someone erased half the skyscrapers from a city skyline, leaving only the faintest outlines behind. So why are these satellites missing? One clue lies in the delicate dance between dark matter and the galaxies it cradles. Simulations assume halos are monolithic, unchanging structures, but reality is messier. When gas collapses to form stars, the resulting supernova unleash torrents of energy, blasting material outward in violent waves. This feedback might puff up dark matter, diluting its density and stunting galaxy growth. Picture trying to build a sandcastle in a rising tide. No matter how carefully you sculpt it, the waves keep washing away your progress. Over billions of years, these feedback loops could transform would-be giants into faint dwarfs, leaving behind a galaxy graveyard of unrealized potential. Yet feedback alone can't explain everything. Some of the Milky Way's surviving satellites, like the Large Magellanic Cloud, are suspiciously massive, flouting expectations just as much as the missing ones. This has led scientists to question whether dark matter halos might be less lumpy than simulations suggest, or if something far stranger is at play. Could the halos themselves be heated up by cosmic collisions, their particles jostled into smoother distributions? Or might dark matter interact with itself in ways we haven't yet imagined, subtly reshaping the rules of gravitational assembly? The implications ripple far beyond our galaxy. If the too big to fail problem persists across the universe, it could mean our simulations are missing a fundamental ingredient, not just in physics, but in the very recipe for cosmic structure. Every failed satellite is a silent critique of our models, urging us to reconsider how dark matter orchestrates the grand ballet of the cosmos. Until we solve this riddle, even the most sophisticated simulations will remain haunted by galaxies that should exist but don't. Where does a dark matter halo actually end? Unlike the crisp boundaries of galaxies where starlight abruptly fades into blackness, halos refuse to play by such neat rules. They taper off like a whisper, their influence extending far beyond what any telescope can see. Astronomers call this fuzzy frontier the virial radius, a mathematical line drawn in the sand where the halo's grip on matter finally weakens enough for objects to escape its pull. But here's the catch, even this boundary isn't fixed. Dark matter particles orbit in vast, chaotic paths, some straying far beyond the virial radius before looping back like cosmic boomerangs. The result, a halo with no true edge, just a gradual thinning, as if the universe itself can't decide where shadow ends and emptiness begins. Compare that to ordinary matter, where edges are stark and unmistakable. A spiral galaxy's disk doesn't fade, it stops, its outer stars halting as abruptly as a cliff plunging into the sea. Gas clouds, too, have clear-cut borders, their atoms either bound by gravity or drifting free. This contrast reveals a fundamental truth. Visible matter clumps and cools, settling into defined structures, while dark matter remains forever restless, its particles too aloof to slow down and condense. It's the difference between a crowd packed into a stadium and smoke dissipating in the wind. One obeys sharp boundaries, the other bleeds into the void. Why does this matter? Because the halo's ambiguous edges hold secrets about dark matter's nature. If particles interacted more strongly, collisions might trim their orbits, creating sharper cutoffs. Instead, their ghostly indifference sculpts halos into diffuse clouds, stretching far beyond where models predict. Some observations even suggest halos might be larger than we thought, with tendrils reaching into intergalactic space, weaving connections between galaxies like invisible threads. This could explain why galaxy clusters move faster than expected. Their halos might be handshaking in the dark, trading gravity across cosmic distances. The search for the halo's edge isn't just academic. It's a hunt for the rules governing the invisible universe. Every stray particle beyond the virial radius is a test of our theories, a challenge to our assumptions. And as telescopes grow sharper, they're revealing a cosmos where darkness doesn't end, it just changes form, blending into the fabric of space-time itself. The lesson: in the realm of dark matter, even emptiness is full of surprises. Black holes and dark matter halos might seem like cosmic strangers. One devours everything in its path, the other ghostly and indifferent. But look closer, and you'll find their fates are tangled in ways that rewrite the rules of gravity itself. Take supermassive black holes, those monstrous anchors at the heart of galaxies. They weigh millions to billions of times more than our sun, yet no one's entirely sure how they grew so large so quickly. Enter dark matter halos, the invisible giants cradling galaxies. Could they be the black hole's secret fuel source? Some theories suggest these halos act like cosmic conveyor belts, funneling dark matter toward the center where it's crushed into oblivion, feeding the black hole's insatiable appetite. Picture a drain at the bottom of an invisible whirlpool. As dark matter particles spiral inward, collisions or rare interactions might strip away their energy, sending them plummeting past the point of no return. But here's where it gets weird. Dark matter doesn't behave like ordinary gas or stars. It's famously aloof, barely noticing normal matter, let alone colliding with itself. So how could it feed anything? One wild possibility involves self-interacting dark matter, where particles occasionally bump into each other, shedding energy and edging closer to the black hole's grasp. Others propose that black holes might warp spacetime so drastically they bend the orbits of passing dark matter particles, trapping them over millennia like a spider's web catching dust. There's even a fringe idea that black holes could convert dark matter into exotic radiation, slowly siphoning its mass away. Yet for all these theories, evidence remains elusive. The Milky Way's central black hole, Sagittarius A, is suspiciously quiet. If it were feasting on dark matter, why isn't it glowing with the energy of annihilation? Then there's the puzzle of black hole mergers. When two galaxies collide, their halos intermingle, but their central black holes eventually pair up, spiraling together in a gravitational tango. LIGO detection of gravitational waves revealed black holes merging across the cosmos, some bizarrely heavy, others spinning faster than physics should allow. Could dark matter be tipping the scales? Simulations show that dense halos might accelerate these mergers, acting like cosmic glue that keeps black holes bound as galaxies jostle around them. Or perhaps dark matter's gravity subtly tweaks the black hole's orbits, nudging them toward collision sooner than expected. The wildest speculation that dark matter isn't just influencing black holes, it might become them. Hypothetical primordial black holes forged in the chaos of the early universe could themselves be dark matter, lurking unseen in halos until they collide and send ripples through space-time. The implications are staggering. If halos and black holes are partners in crime, it would mean dark matter isn't just a passive scaffold, it's an active player in shaping the universe's most violent events. Every merger, every quasar's outburst might carry fingerprints of the invisible cosmos. Yet for now, the relationship remains a cosmic game of whispers, where gravity is the only language both sides seem to speak. Until we crack that code, the dance between darkness and oblivion will keep its secrets. To understand how dark matter halos came to be, we have to rewind the cosmos nearly 13.8 billion years, back to a time when the universe was nothing but a seething cauldron of energy, hotter and denser than the heart of a star. In those first fleeting moments after the Big Bang, the seeds of today's halos were already being sown. Tiny quantum fluctuations, random ripples in the fabric of space-time, stretched and amplified as the universe expanded, creating microscopic variations in density. Think of it like blowing up a balloon with faint ink spots. As it inflates, those tiny marks grow into sprawling patterns. Dark matter, ever the silent architect, was uniquely poised to latch onto these irregularities. While ordinary matter was busy bouncing off photons in the primordial plasma, dark matter, unaffected by light's push and pull, could start clumping together almost immediately, laying the invisible groundwork for everything to come. But how did those faint whispers of density blossom into the vast halos we see today? The answer lies in gravity's relentless patience. Over millions of years, slightly denser regions pulled in more dark matter, growing heavier and hungrier, while emptier patches were left behind. This cosmic snowball effect created a web of filaments and voids, a scaffolding known as the cosmic web, with halos forming at the intersections like dewdrops on a spider's silk. Simulations of this process look eerily organic, as if the universe itself is breathing, drawing matter into its lungs only to exhale it into structured patterns. The largest halos became the nurseries for galaxy clusters, while smaller ones seeded individual galaxies, each one a gravitational well waiting to be filled with stars. Yet even this elegant picture has its wrinkles. Some models suggest halos didn't grow steadily but in violent spurts, merging and cannibalizing each other in a chaotic dance. Others propose that dark matter's peculiar properties, whether it's warm, cold, or something stranger, left distinct fingerprints on halo formation. Warm dark matter, for instance, would have smeared out small-scale structures, leaving fewer dwarf galaxies in its wake, while cold dark matter predicts a universe teeming with them. The fact that we're still debating this means the early universe might have been far wilder than our simulations can capture. Perhaps the most tantalizing clue comes from the cosmic microwave background, the afterglow of the Big Bang. Faint temperature variations in this ancient light reveal the exact spectrum of those primordial density fluctuations, matching predictions almost perfectly. But almost is the operative word. There are subtle discrepancies, tiny deviations that could hint at entirely new physics. Could dark matter have interacted with other forces in its youth? Might there have been not one but multiple types of dark matter, each leaving its mark on the growing halos? Every new observation peels back another layer, revealing a cosmic origin story far richer and stranger than we ever imagined. The birth of halos isn't just a history lesson. It's a key to understanding why the universe looks the way it does today. Those early density ripples didn't just shape dark matter. They set the stage for every galaxy, every star, every planet. Without halos, the night sky would be an empty abyss. So the next time you gaze up at the Milky Way, remember, you're not just seeing stars, you're witnessing the afterlife of quantum whispers from the dawn of time. Simulations paint a picture of the Milky Way as a cosmic monarch, ruling over a swarm of thousands of satellite galaxies, each one nestled in its own dark matter halo, like fireflies circling a lantern. Yet when astronomers peer into the night sky, they find a far emptier kingdom. Instead of the predicted multitude, only about 60 of these satellites have been spotted, a glaring mismatch dubbed the missing satellites problem. This isn't just a census error, it's a crisis for our understanding of how dark matter structures the universe. If halos are as abundant as simulations suggest, where are all their galactic guests? One explanation hides in the shadows literally. Many of these satellites could be too faint for current telescopes to detect. Picture trying to spot a candle flame next to a spotlight. The Milky Way's brilliance drowns out its dimmer companions. Recent surveys like the Dark Energy Survey have uncovered ultra-faint dwarfs, galaxies so diffuse they're barely more than a handful of stars held together by dark matter. These ghosts might account for some of the discrepancy, but even adding them to the tally leaves hundreds of halos unaccounted for. It's as if the universe built a sprawling neighborhood but forgot to move in most of the residents. Then there's the question of survival. Not all halos may have retained their stars. Some could have been shredded by tidal forces, their stars scattered into faint streams like cosmic breadcrumbs. Others might have had their gas, the raw material for star formation, stripped away by the Milky Way's gravitational pull, leaving them dark and inert. Imagine a tree shedding leaves. These failed halos would be nearly invisible, detectable only by their gravitational whispers. Yet even this destruction can't fully explain the gap. Simulations that include these processes still overpredict the number of visible satellites, suggesting something fundamental is missing from our models. The plot thickens when we consider dark matter's behavior. If it's warmer or more dynamic than assumed, small halos might never accumulate enough gas to ignite stars, leaving them eternally dark. Alternatively, early radiation from the first galaxies could have sterilized neighboring halos, preventing star formation altogether. It's a cosmic catch-22. The very processes that make galaxies bright enough to see might also erase their smaller siblings. What's at stake isn't just a head count. This discrepancy forces us to confront whether we've misunderstood dark matter's nature, the physics of galaxy formation, or both. Every missing satellite is a silent challenge to our theories, a reminder that the universe's blueprint is still riddled with erasures we can't yet decipher. Until we solve this puzzle, the true population of galactic satellites and the halos that host them will remain one of cosmology's most persistent ghosts. If dark matter is truly as ghostly as we think, why do some galaxies behave like they're swimming through cosmic molasses? That's the million-dollar question behind one of the most heated debates in astrophysics, whether dark matter particles interact with each other, not just with gravity. For decades, the reigning assumption was simple: dark matter is collisionless. Like ships passing in the night, its particles should glide past one another without a whisper of contact. But a handful of bizarre cosmic smash-ups have thrown that idea into doubt. Take the Bullet Cluster, the poster child for dark matter's weirdness. When these two galaxy clusters collided, their dark matter halos sailed right through the wreckage unfazed while the visible gas piled up like a traffic jam. At first glance, this seemed like perfect proof of dark matter's aloofness until researchers noticed something odd. The halos weren't entirely unscathed. One appeared slightly lagging, as if it had hit a patch of invisible glue. This tiny hiccup sparked a radical idea. What if dark matter does interact just barely? Picture two dancers waltzing through a ballroom. Normally, they'd never touch, but if their sleeves were lightly dusted with syrup, they might occasionally brush against each other, slowing their momentum without fully stopping. That's the essence of self-interacting dark matter, or SIDM. A theory suggesting dark matter particles might nudge each other through some unknown force, leaving no trace except a faint gravitational drag. Supporters point to other clusters like Able 3827, where dark matter seemed to trail behind its galaxy by a hair, as if something had tugged it mid-collision. Even more telling, the way some dwarf galaxies' halos appear fluffier than expected. Their cores softened like butter left in the sun, exactly what you'd predict if dark matter particles were scattering off one another over billions of years. But critics aren't convinced. They argue these anomalies could just be quirks of gravity or measurement errors. After all, if dark matter is sticky, why don't we see more dramatic delays in every cluster collision? And why haven't underground detectors, tuned to catch even the faintest whispers of particle interactions, found a shred of evidence? The truth might lie somewhere in between. Perhaps dark matter isn't completely oblivious to its kin, just nearly so, interacting once in a blue moon under extreme conditions. Or maybe it's a mix of particles, some sociable, others loners, like a crowd where a few people occasionally bump elbows while the rest keep their distance. The implications are colossal. If dark matter collides even weakly, it could explain why some halos look puffy or why small galaxies lack the dense cores simulations predict. It might even hint at a hidden sector of physics where dark matter communicates through forces beyond our current theories. Every galaxy cluster collision is now a forensic lab for this cosmic detective story, each one scrutinized for the faintest smear of stickiness in the dark. Until we catch these phantoms red-handed or prove they're truly solitary, the question remains. Is the universe's hidden architecture built with ghostly bricks, or is there a shadowy scaffolding we've yet to fully fathom? If dark matter halos are the invisible skeletons of galaxies, shouldn't they move like them too? Here's the twist. While stars and gas whirl in elegant disks, halos might be dancing to a far stranger rhythm. Angular momentum, the same force that makes a figure skater spin faster as they pull their arms in, should, in theory, be shared between visible matter and its dark counterpart during galaxy formation. Yet when astronomers try to measure the rotation of dark matter halos, they're met with a cosmic riddle. Some halos seem to spin in sync with their galaxies, like partners in a waltz. Others lurch drunkenly, their axes tilted or their motion chaotic, as if the music of the universe skipped a beat. How does this misalignment happen? Picture the early universe as a swirling storm of gas and dark matter. As gravity pulls these ingredients together, they should exchange momentum like two hands clasping and spinning in unison. But dark matter doesn't feel friction or pressure, so it resists settling into an orderly disk. Instead, it lingers in a messy, puffed-up cloud, its rotation imprinted by the primordial tides of the cosmos. Simulations suggest these halos might spin lazily, completing a full rotation only once every 10 billion years, far slower than the Milky Way's disk, which spins like a carousel every 200 million years. Even weirder, some halos might not rotate coherently at all. Instead of a unified whirl, their particles could orbit in conflicting directions, like crowds crossing a busy intersection, cancelling out any net spin. The stakes are high. If halos and galaxies spin independently, it challenges the textbook story of galaxy formation, where angular momentum is neatly conserved. Instead, it hints at a messy, improvisational process where mergers, gas flows, and even dark matter's quirks tug the cosmic choreography offbeat. Take the Milky Way's halo. Studies of its outer reaches suggest it might be rotating, but not around the same axis as the galactic disk. Imagine a spinning top wobbling inside a hula hoop, each moving to its own rhythm. What's behind this mismatch? One clue lies in galactic cannibalism. When a large galaxy devours a smaller one, their halos don't just blend smoothly, they tangle, transferring momentum in unpredictable ways. The result? A halo spin might end up tilted or even reversed, like a record spinning the wrong way. Another possibility: dark matter might carry a fossil memory of the universe's infant turbulence, its rotation locked in by ancient density waves that had nothing to do with the galaxies forming inside it. The implications ripple beyond astronomy. If halos spin differently than expected, it could affect how galaxies cluster, how black holes feed, even how we map the invisible web of dark matter binding the cosmos. Every misaligned rotation is a clue not just to how halos move, but to the forces that shaped them in the darkness before the first stars flickered to life. And until we solve this puzzle, the universe's grand choreography remains half hidden, its darkest dancers moving to a rhythm we're only beginning to hear. Dark matter and dark energy are locked in a cosmic tug-of-war, with the fate of the universe hanging in the balance. On one side, dark matter's relentless gravity pulls galaxies and clusters together, sculpting vast halos that act as the universe's hidden framework. On the other, dark energy pushes everything apart, accelerating the expansion of space itself like an unstoppable force. This isn't just a quiet standoff, it's a battle that could reshape the cosmos over billions of years, bending even the most massive halos to its will. Think of it like a rubber sheet stretched taut. Dark matter's gravity creates deep wells in that sheet, trapping galaxies like marbles in a bowl. But dark energy stretches the sheet itself, making it flatter and wider over time. The deeper the wells, the harder dark matter fights to hold everything together, yet dark energy's influence grows stronger as the universe expands, its mysterious push becoming undeniable. This raises a haunting question. What happens to dark matter halos when the fabric of space is being yanked apart beneath them? Some simulations suggest halos might slowly evaporate, their outer edges torn away by the accelerating expansion, leaving behind denser but smaller cores. Others propose that while the largest halos, those anchoring galaxy clusters, will cling to their structure, smaller ones could be ripped apart entirely, their dark matter scattered into the void. It's like watching sandcastles face an incoming tide. The mightiest towers might endure, but the smaller structures dissolve without a trace. Yet there's a twist. Dark energy's expansion isn't uniform. In regions where dark matter's gravity is strongest, like the hearts of superclusters, its pull can resist dark energy's influence, creating cosmic fortresses that linger longer than the rest. Meanwhile, the emptier voids between galaxies stretch faster, becoming ever more desolate. This growing imbalance could lead to a future where the universe isn't just expanding, it's fracturing, with isolated islands of matter floating in an ever-widening sea of darkness. The stakes couldn't be higher. If dark energy's grip tightens, it won't just affect halos, it could dictate whether galaxies, stars, and even atoms themselves are ultimately torn apart. Some theories even suggest dark energy and dark matter might be two faces of the same enigmatic force, changing their behavior over cosmic time. Until we understand their true nature, the universe's ultimate fate remains shrouded in mystery, a silent war waged in the shadows where the invisible decides the destiny of everything we see. If dark matter halos are the universe's oldest structures, could some of them be cosmic newborns? We often picture these invisible giants as relics of the Big Bang, frozen in time since the cosmos was a seething infant plasma. But the universe never stops evolving, and there's tantalizing evidence that halos might still be forming today, rewriting the rules of cosmic growth. Imagine a river carving new channels long after the flood has passed. While most halos crystallized billions of years ago, others could be emerging in the voids between galaxies where dark matter's dance is far from over. The key lies in the cosmic web's quieter corners. In dense regions like galaxy clusters, dark matter's gravitational tug-of-war ended eons ago, leaving halos locked in stable configurations. But in the emptier stretches of space, the so-called voids, conditions are ripe for late arrivals. Here, delicate filaments of dark matter slowly twist and knot under their own gravity, like strands of syrup thickening in cold water. These late-forming halos wouldn't resemble the behemoths anchoring galaxies. Instead, they'd be faint, diffuse, and eerily pristine, untouched by the violent mergers that shaped their ancient cousins. Spotting them, however, is like trying to photograph a shadow in moonlight. That's where gravitational lensing offers a ghostly glimpse. When light from distant quasars passes through these regions, subtle distortions in its path might betray the presence of young halos too faint to see directly. Some astronomers argue that certain empty patches of space bend light more than expected, as if invisible fingers are pressing gently on spacetime's fabric. Other clues come from rogue stars, lonely suns drifting far from any galaxy, whose paths could be swayed by nascent halos coalescing around them like invisible nets. Yet not everyone's convinced. Critics point out that the universe's expansion makes it harder for halos to form late. Dark energy stretches space like taffy, pulling matter apart faster than gravity can gather it. For a halo to overcome this cosmic tug-of-war today, it would need a perfect storm of density, a rare alignment of dark matter streams converging against all odds. Simulations suggest these late bloomers might exist, but they'd be the exception, not the rule. Cosmic underdogs fighting an uphill battle against the universe's relentless thinning. The implications ripple beyond curiosity. If young halos are real, they'd challenge our models of dark matter's behavior, hinting that it clumps differently in quieter cosmic environments. They might also solve the puzzle of ultra-diffuse galaxies, faint, wispy islands of stars that seem to float untethered, possibly cradled by halos born out of time. Every potential sighting is a window into dark matter's hidden life cycle, proving that even in the cosmos's quietest corners, the invisible universe never stops rewriting its own story. One of the most enduring puzzles about dark matter halos isn't just where they end, but how their weight is distributed from core to edge. Picture a mountain with an impossibly steep peak that flattens abruptly into rolling foothills, yet somehow grows denser again in its outer reaches. That's the bizarre density profile predicted by the Navarro-Frank-White model, or NFW, the gold standard for mapping how dark matter piles up in halos. Named after the three astrophysicists who pioneered it in the 1990s, this mathematical framework suggests halos should be densest at their centers, with matter thinning out smoothly toward the edges, but not in a way that intuition would expect. Instead of fading evenly, the NFW profile has a cusp-core, plunging sharply inward, followed by a gentler decline that still leaves the halo's outskirts far weightier than they appear. For massive galaxy clusters, this model fits beautifully. Observations of gravitational lensing and galaxy motions align nearly perfectly with NFW's predictions, as if dark matter obediently followed the cosmic recipe. But venture into the realm of smaller, dimmer galaxies and the theory starts to unravel. Ultra-diffuse galaxies, those ethereal, almost translucent islands of stars should, according to NFW, be anchored by halos with dense, compact cores. Instead, many of them flaunt fluffy centers where dark matter seems conspicuously diluted, as if someone hollowed out the middle. It's like biting into a chocolate truffle only to find the center isn't rich ganache but whipped air. Why the mismatch? One camp argues the NFW profile isn't wrong, it's just incomplete. Ordinary matter, often overlooked in pure dark matter simulations, might be the disruptor. When gas collapses to form stars, supernova explosions can unleash torrents of energy, blasting waves through the halo that push dark matter outward, eroding its dense core over time. Imagine shaking a snow globe vigorously. The flakes won't stay settled at the bottom. Similarly, repeated stellar fireworks could puff up a halo's center, transforming what should be a spike into a shallow bowl. Others suspect the issue lies deeper in dark matter's fundamental nature. If particles interact weakly with each other, bumping and scattering like shy dancers in a crowded room, they could naturally smooth out those overgrown cusps into gentler cores. Then there's the radical fringe proposing that gravity itself behaves differently on galactic scales, rendering NFW obsolete. Yet none of these explanations cleanly solves the puzzle. Dwarf galaxies with cores too diffuse for NFW often neighbor others that fit the profile snugly, as if the universe is taunting us with exceptions. The stakes are higher than a theoretical tweak. If the NFW profile fails for certain galaxies, it could mean halos aren't one-size-fits-all structures but products of their environment, shaped by interactions we've barely begun to map. Or worse, that dark matter is far more complex than a single, sluggish particle. Every ultra-diffuse galaxy with a defiantly fluffy core is a crack in the foundation of our cosmic understanding, a whisper that the invisible machinery of the universe might be stranger and more intricate than we ever imagined. Could the invisible hand of dark matter have played a role in the birth of life itself? It's a staggering thought that the same elusive substance shaping galaxies might also have subtly guided the conditions for planets, oceans, and even biology. At first glance, the idea seems outlandish. Dark matter doesn't interact with light or chemistry, so how could it possibly influence something as delicate as life? Yet when we follow gravity's trail, the connections become harder to ignore. Take our own solar system. The Milky Way's vast halo didn't just sculpt our galaxy's spiral arms, it also set the stage for Earth's formation. Billions of years ago, as the halo's gravitational pull funneled gas and dust into our corner of space, it created dense molecular clouds where stars like the Sun could ignite. But here's the twist: without dark matter's steadying influence, those clouds might have scattered too thin or collapsed too violently. The halo's gravity acted like a cosmic moderator, ensuring star formation wasn't too chaotic or too sparse, but just right for rocky planets to coalesce in stable orbits. Even more intriguing is dark matter's possible role in shielding fledgling solar systems from catastrophe. Some theories suggest that halos act as gravitational buffers, deflecting wayward stars and gas clouds that could have destabilized planetary orbits. Imagine a protective bubble, invisible yet vital, keeping young worlds safe from the universe's chaos long enough for life to take root. There's even evidence that our solar system's periodic trips through the Milky Way's denser dark matter regions, occurring roughly every 30 million years, might coincide with mass extinctions. Could fluctuations in dark matter density have nudged comets from the Oort cloud, sending them hurtling toward Earth in catastrophic impacts that reshaped evolution? The implications stretch beyond our galaxy. In regions where dark matter halos are too massive or too sparse, star formation might veer toward extremes, either blazing giants that burn out too quickly for life to emerge, or dim red dwarfs with inhospitable tidal-locked planets. It's as if the universe has a hidden recipe for habitable worlds, and dark matter is the quiet sous chef, measuring out gravity's ingredients with unseen precision. Of course, this is still speculative territory. No one's claiming dark matter wanted life to exist, but if its gravitational scaffolding set the table for chemistry to unfold, then every living thing, from microbes to minds, might owe a silent debt to the universe's most mysterious substance. The next time you gaze up at the stars, remember, the darkness between them isn't empty. it might just be the reason you're here to see it at all. Magnetism is one of the universe's most pervasive forces, sculpting everything from solar flares to the delicate migrations of birds. But could it also weave through the invisible realms of dark matter halos? The idea sounds like science fiction after all. Dark matter famously ignores electromagnetic forces. Yet recent theories suggest these halos might harbor their own cryptic versions of magnetic fields, bending the rules of physics in ways we're only beginning to fathom. At the heart of this mystery lies a radical concept: dark photons. Unlike the photons we know, particles of light that paint the cosmos in color, dark photons would be shadowy messengers carrying a hidden form of electromagnetic energy detectable only through their gravitational echoes. If they exist, these phantom particles could allow dark matter to generate subtle magnetic fields, not through the familiar push and pull of charges, but through interactions entirely alien to our standard model. Picture a world where magnetism operates in whispers, unseen yet powerful enough to nudge entire galaxies. The implications are dizzying. If halos generate even faint magnetic fields, they could leave fingerprints on the cosmic microwave background, the afterglow of the Big Bang. Certain anomalies in this ancient light, like unexpected swirls or polarized patterns, might betray dark magnetism at work. Others speculate these fields could influence how galaxies rotate, subtly tweaking the speeds of stars in ways that defy conventional gravity. The most tantalizing clue comes from fast radio bursts, mysterious, high-energy blips from across the universe. Some of these signals show strange distortions as they travel, as if passing through invisible, magnetized veils. Could halos be the culprits, their phantom fields bending space itself? Skeptics, of course, have their doubts. If dark photons exist, why haven't particle colliders spotted them? Why doesn't every galaxy show the same magnetic quirks? The answers might lie in scale. Unlike the Milky Way's turbulent magnetic web, woven by supernova and swirling gas, halo fields would be vast and diffuse, imprinting themselves over eons rather than centuries. Detecting them would require instruments sensitive to the universe's slowest, subtlest rhythms, like listening for a heartbeat through layers of cosmic static. The hunt is already underway. Experiments like CERN NA-64 are firing beams of particles into oblivion, hoping to catch a glimpse of dark photons transforming into ordinary ones. Meanwhile, radio telescopes scour the skies for anomalies in polarized light, searching for the faintest traces of magnetism where none should be. Every null result narrows the possibilities, but every anomaly sparks fresh debate. Whether halos wield magnetic fields or not, the pursuit itself is illuminating. It forces us to ask, if dark matter truly shapes the cosmos, why wouldn't it leave more than just gravitational footprints? Perhaps the universe's greatest structures don't just hide in the dark, they hum with energies we've yet to name. Dark matter halos don't exist in isolation. They gather in cosmic neighborhoods, weaving an intricate web that stretches across the universe. Picture a bustling city where skyscrapers cluster in downtown cores, while suburbs sprawl outward in looser formations. Halos arrange themselves in much the same way, with smaller ones flocking around larger ones like moths to a flame, creating a hierarchy that mirrors the visible universe's structure. This pattern, known as the halo occupation distribution, isn't just a curiosity. It's a blueprint for how galaxies grow, collide, and evolve over billions of years. Zoom out far enough, and you'll see halos congregating in superclusters, colossal assemblies of galaxies bound by gravity, each one tethered to an even vaster dark matter framework. These superclusters resemble neurons in a cosmic brain, with filaments of halos connecting dense nodes where galaxies swarm in unimaginable numbers. The Virgo supercluster, home to our Milky Way, is just one such metropolis in a universe teeming with them. But how do halos decide where to settle? The answer lies in the early universe's faint density fluctuations. Regions slightly denser than their surroundings attracted more dark matter, growing into the hubs we see today, while emptier areas became the voids between them. What's fascinating is how this distribution shapes galaxies. A halo's position in the cosmic web determines its destiny. Those in dense clusters face violent lives, frequently colliding with neighbors or having their gas stripped away by intergalactic winds. Meanwhile, halos in quieter outskirts grow slowly, their galaxies evolving in relative peace. This explains why galaxies in clusters tend to be elliptical, older, redder, and gas-poor, while those in the cosmic boondocks often remain spirals, rich with star-forming fuel. The halo occupation distribution isn't just a map, it's a fortune teller predicting a galaxy's fate based on its address in the universe. Yet the plot thickens when we compare theory to observation. Simulations predict halos should cluster in precise ways, but reality throws curveballs. Some galaxy groups have fewer halos than expected, as if dark matter skipped town. Others, like the mysterious dark galaxies devoid of stars, seem to have halos with no visible residents. These discrepancies hint at untold stories. Perhaps dark matter's properties are more complex, or maybe baryonic physics is reshaping halos in ways we don't yet understand. The cosmic web isn't static either. Halos migrate over time, drawn into clusters by gravity's pull, their journeys etching the universe's large-scale structure in real time. By studying their motions, astronomers can trace the web's hidden currents, much like tracking ocean tides by watching drifting buoys. Every halo's place in this grand network is a clue not just to dark matter's nature, but to how the universe itself grew from a whisper of quantum noise into the sprawling tapestry we see today. The neighborhoods of the cosmos are anything but random. They're the fingerprints of gravity's patient, invisible hand. Deep in the heart of dark matter halos, a violent cosmic drama might be unfolding, one we can't see but might just be able to hear. The theory of dark matter annihilation hinges on a provocative idea. What if these elusive particles don't just pass through each other like ghosts, but occasionally collide with enough fury to destroy themselves? When matter meets antimatter, they obliterate each other in a flash of energy. If dark matter behaves similarly, even rarely, the resulting gamma rays could be our best chance to catch these phantoms red-handed. Gamma rays, the universe's most energetic light, are the smoking gun. Unlike visible photons, which dark matter famously ignores, these high-energy bursts could betray annihilation events happening right now in the Milky Way's halo. Picture two invisible particles locking in a death spiral, vanishing in a silent explosion that sends gamma rays screaming across space. Telescopes like Fermi-LT have spent years scouring the sky for these telltale flashes, focusing on regions where dark matter should be densest, the centers of galaxies, dwarf satellites, and the diffuse edges of our own halo. The search has turned up tantalizing hints. One of the most debated signals comes from the galactic center, where an excess of gamma rays defies explanations from known astrophysical sources like pulsars or cosmic rays. Could this be dark matter's faint scream, or just the chatter of mundane celestial physics? The controversy rages, but the signal's distribution, peaking where models predict the highest dark matter density, keeps theorists intrigued. Even more compelling are dwarf galaxies like Draco and Reticulum II, which emit faint gamma glows despite having almost no gas or stars to produce them. These cosmic ghost towns are 99% dark matter, making them pristine laboratories for annihilation. Yet for every hopeful clue, there's a confounding twist. If gamma rays are the key, why haven't we seen them in all halos? Some propose that dark matter annihilates only under specific conditions, perhaps requiring rare particle types or energies. Others suggest the signals might be drowned out by background noise, like trying to hear a whisper in a hurricane. The most radical possibility: we've been searching for the wrong fingerprint altogether. Annihilation might produce not just gamma rays but exotic particles like neutrinos, or even distort the cosmic microwave background in ways we've yet to detect. The hunt is far from over. Next-generation telescopes like the upcoming Cherenkov Telescope Array will scan the skies with unprecedented precision, while underground detectors watch for secondary particles from annihilation events. Whether these efforts succeed or fail, the implications are profound. A detection would crack open dark matter's identity, revealing not just its existence but its behavior. Silence, on the other hand, might force us to ask an even deeper question. If dark matter isn't annihilating, what other invisible laws govern its shadowy realm? The answer, whatever it is, lies hidden in the halo's darkest corners waiting. Is dark matter a cosmic fog or a swarm of invisible boulders? That's the essence of the fuzzy versus chunky debate, a battle over whether the universe's missing mass is made of particles so light they behave like a misty quantum field or so heavy they lumber through space like phantom asteroids. The answer isn't just academic, it shapes how we interpret the very structure of dark matter halos, especially on the smallest scales. Fuzzy dark matter proposes particles trillions of times lighter than electrons, their wave-like nature smoothing out halos into ethereal, diffused clouds. Picture dropping a pebble into a pond. The ripples that spread out are tiny, close together, and delicate. On galactic scales, this fuzziness would prevent small clumps from forming, leaving halos with fewer satellite galaxies and softer edges, a match for some of the missing satellite anomalies we observe. But chunky dark matter tells a different story. If the particles are hefty, think WIMP, or weakly interacting massive particles, they'd stamp halos with sharp, dense substructures like boulders hidden under a blanket. Simulations of this scenario predict halos should be teeming with countless tiny subhalos, each a gravitational knot waiting to host a dwarf galaxy. Yet when astronomers count these satellites, the numbers fall short. This tension has led some to wonder, is reality fuzzy or are we missing a piece of the puzzle? The evidence is as contradictory as it is compelling. On one side, ultra-diffuse galaxies with their wispy, spread-out stars seem to float in halos that mirror the fuzzy prediction their dark matter too smooth and shallow to anchor dense stellar cores. On the other, certain lensing observations reveal halos with lumpy gravitational fields, as if chunky dark matter is casting subtle shadows on passing light. Even the cosmic microwave background offers mixed signals. Its patterns align broadly with cold, chunky dark matter, but the slight smudges in its polarization maps could hint at something more nuanced, a universe where dark matter isn't purely one or the other, but a spectrum of possibilities. Experiments are racing to settle the debate. Action hunters like the Adams Project tune their detectors to catch the faint hum of hypothetical fuzzy particles oscillating in magnetic fields. Meanwhile, telescopes scour dwarf galaxies for gamma rays that might betray the self-destruction of chunky WIMP. The stakes couldn't be higher. If dark matter is fuzzy, it would revolutionize particle physics, implying entirely new forces and dimensions. If it's chunky, we're back to the drawing board on why small-scale structures don't match simulations. The irony, both theories could be wrong. Some physicists speculate dark matter might be a mix of heavy and light particles or something else entirely, an idea that would force us to rewrite cosmology from scratch. Until we know, halos remain the universe's most enigmatic sculptures, their true texture hidden in the dark. Why do some galaxies blaze with the fiery arms of spirals, while others fade into featureless elliptical blobs or twist into chaotic, irregular shapes? The secret might lie in the invisible hands of their dark matter halos, cosmic puppeteers shaping galactic destinies through gravity's silent pull. Consider the Milky Way, its spiral arms shimmering with newborn stars, tracing elegant curves like water spiraling down a drain. This beauty isn't accidental. Spiral galaxies tend to nest within halos that rotate steadily, their angular momentum preserved over billions of years. As gas and dust cascade into these spinning halos, friction slows the material, flattening it into a disk where stars can form in orderly arms. The halo acts like a potter's wheel, its rotation molding the galaxy into a delicate cosmic pinwheel. But halos aren't all graceful whirls. Elliptical galaxies, those football-shaped relics devoid of spiral structure, tell a darker story. These galaxies often reside in halos that endured violent pasts, where mergers or close encounters scrambled their rotation into chaos. Picture two dancers colliding mid-spin. Their coordinated motion dissolves into random movement. When halos collide, their gas clouds smash together, triggering frenzied star formation that burns through fuel too quickly, leaving behind a red and dead elliptical. The halo's turbulent history imprints itself on the galaxy it hosts, turning stellar elegance into gravitational wreckage. Then there are the misfits, irregular galaxies, their stars scattered like shards of broken glass. These galaxies often occupy halos too small or isolated to gather gas efficiently, or ones disturbed by larger neighbors' gravitational tides. Without a dominant rotation or the violent climax of a merger, they become cosmic doodles, unfinished sketches in the universe's gallery. But mass plays a starring role too. The heftiest halos, those anchoring galaxy clusters, often host monstrous ellipticals at their cores, their growth fueled by cannibalizing smaller galaxies. Meanwhile, mid-sized halos like the Milky Way's favor spirals, their mass just right to sustain steady star formation without descending into chaos. The tiniest halos might never form galaxies at all, their gravity too weak to corral enough gas to ignite stars, leaving them dark and silent. The exceptions, though, are where the mystery deepens. Some ultra-diffuse galaxies float in massive halos yet remain ghostly and sparse, defying the expectation that more dark matter means more stars. Others, like the ancient dead spirals found in deep surveys, spin peacefully in halos that should have torn them apart. These outliers suggest that while halos set the stage, the play of baryonic physics, supernova, black holes, magnetic fields writes its own unpredictable script. The lesson here, a galaxy's form isn't just about the halo it lives in, but the life it's lived. Dark matter may be the invisible director, but ordinary matter is the actor, improvising within gravity's grip. Together, they perform a cosmic ballet, one where every pirouette, collision, and stumble leaves a lasting mark on the universe's grand stage. The universe is a vast, interconnected network where rivers of dark matter flow silently through the cosmic web, feeding hungry halos like invisible rainfall. These streams, known as cosmic filaments, are the highways along which dark matter travels, thread-like structures stretching millions of light years, connecting galaxy clusters in a delicate lattice of gravity. But what happens when these filaments meet a dark matter halo? Some theories suggest the halo acts like a cosmic funnel, drawing in dark matter particles in a steady drizzle, or even a torrential downpour, depending on the density of the surrounding web. This process, called accretion, could be the hidden engine behind galaxy growth, fueling halos with fresh dark matter over billions of years and shaping their evolution in ways we're only beginning to grasp. The idea of dark matter, rain, isn't just poetic. It's grounded in sophisticated simulations of the universe's large-scale structure. Picture a sponge soaking up water. As filaments intersect with a halo, gravity pulls dark matter inward, channeling it along these invisible rivers. Cold dark matter, being slow-moving, would trickle in gradually, settling into the halo's outskirts before spiraling toward the center. Warmer varieties, though, might stream in faster, like a sudden summer storm, their higher velocities preventing them from clumping as tightly. The difference leaves distinct imprints on a halo's structure, subtly altering its density profile and rotation. But accretion isn't always gentle. When halos collide or pass through dense knots in the cosmic web, the influx of dark matter can turn violent, triggering shockwaves that ripple through the halo's interior. These cosmic downpours might even spark bursts of star formation, as the sudden gravitational surge compresses gas clouds into newborn stars. some astronomers speculate that the Milky Way's own halo might still be soaking up dark matter from nearby filaments, a slow-motion deluge that's been ongoing since the galaxy's birth. Evidence for this could lie in the odd motions of stars at the galaxy's edge, their orbits subtly perturbed by the gravitational tug of incoming dark matter. Yet mysteries abound. If dark matter rains so steadily into halos, why haven't all galaxies ballooned into monstrous sizes? One possibility is feedback energetic processes like supernova or active galactic nuclei blasting material outward, counteracting the infall. Another is that filaments aren't eternal. As the universe expands, some may stretch to the breaking point, their streams thinning into nothingness before they can fully replenish a halo's reserves. The most tantalizing question of all, could this rain carry clues about dark matter's true nature? If particles interact even faintly, their trajectories as they pour into halos might leave detectable patterns, like the way raindrops scatter differently in a breeze versus a gale. Observing this cosmic rainfall directly is a monumental challenge, but astronomers aren't without tools. Gravitational lensing surveys could reveal distortions caused by dense filaments feeding into halos, while simulations track how different accretion modes sculpt halo shapes over time. The James Webb Space Telescope might even spot the downstream effects, galaxies growing lopsided as dark matter streams in unevenly, or faint stellar trails marking where gas was stirred by a passing filament. Every new observation peels back another layer, revealing a universe where darkness isn't static but dynamic, a place where halos grow not just from ancient seeds, but from the endless, invisible rain threading the cosmos. Some of the most haunting relics in our galaxy aren't stars or planets, they're the ghostly remains of dwarfs long dead, stretched into ribbons of light by the Milky Way's relentless gravity. These stellar streams are the cosmic equivalent of crime scene tape, marking where smaller galaxies were ripped apart and digested by our halo's invisible pull. The most famous, the Sagittarius stream, wraps around the Milky Way like a tattered scarf, its stars tracing a path that betrays dark matter's hidden hand with every orbit. Picture a galaxy as a swarm of bees. When a dwarf galaxy strays too close to a giant like the Milky Way, gravity's tidal forces act like an immense pair of hands, plucking stars away in opposite directions. Over billions of years, these stars form elongated rivers, some spanning hundreds of thousands of light years that continue to orbit long after their parent galaxy is gone. But here's the twist: these streams don't just drift aimlessly. Their paths are exquisitely sensitive to the halo's gravitational quirks, bending and warping in response to invisible lumps and gaps in the dark matter distribution. It's like watching smoke curls reveal the airflow in an unseen wind. The Sagittarius stream is a masterclass in this gravitational archaeology. Born from a dwarf galaxy that ventured too close some 4 to 8 billion years ago, its stars now form a sprawling loop that intersects the Milky Way's disk. But the stream isn't smooth, it's kinked and twisted with clumps of stars moving at odd velocities. These imperfections are forensic evidence pointing to dark matter substructure, small, dense pockets of halo material that tugged on the stream like invisible rocks in a river. Some researchers even speculate the distortions hint at a historic encounter with a massive, unseen object, perhaps a rogue subhalo that barreled through the Milky Way's outskirts, leaving gravitational scars in its wake. Stellar streams aren't just relics, they're real-time experiments. By measuring how their stars move, astronomers can map the halo's gravitational field in 3 dimensions, revealing where dark matter is concentrated and where it's suspiciously absent. Take the Orphan stream, another shredded dwarf whose stars move faster than models predict. The discrepancy suggests our halo might be less dense at its edges than simulations assumed, or that dark matter particles interact in ways that puff up the halo's outer layers. Even stranger, some streams show gaps where stars are missing entirely, as if something invisible took a bite out of the ribbon. Could these be signs of primordial black holes lurking in the halo, or dark matter clumps too faint to see? The stakes go beyond our galaxy. If streams confirm that halos are lumpier than predicted, it might mean dark matter is warmer or more dynamic than we thought. If they're smoother, perhaps our theories about cosmic structure formation need revisiting. Every new stream discovered, like the faint Phoenix stream spotted in 2020, adds another data point to this grand celestial puzzle. These phantom rivers are more than graveyards of lost galaxies. They're the universe's way of sketching its own dark matter blueprint, one stolen star at a time. What happens to a dark matter halo when the universe itself is dying? The answer depends on forces far beyond gravity, forces that could stretch, shred, or dissolve these invisible giants over timescales so vast they dwarf the age of the cosmos. If dark energy continues accelerating the universe's expansion unchecked, halos might face a slow but inevitable evaporation. Picture a sandcastle on a beach as the tide rushes in. At first, the outer grains wash away, then the walls crumble, until finally even the sturdiest towers collapse into the surf. Similarly, as space stretches faster than gravity can counter, a halo's outermost particles would drift beyond its gravitational grip, leaving behind an ever-shrinking core. Current models suggest the Milky Way's halo could lose up to half its mass over the next 100 billion years, its edges fraying into the void like smoke dissipating in the wind. But evaporation isn't the only possible fate. In a hypothetical Big Rip scenario where dark energy's push grows so strong it tears apart galaxies, stars, and even atoms, halos wouldn't just fade, they'd be annihilated in a catastrophic instant. The ripping of spacetime would overcome even dark matter's gravitational bonds, scattering particles beyond any hope of reunion. It's a violent end, one where the universe's invisible scaffolding doesn't just collapse but is erased from existence itself. Not all theories are so bleak. If dark energy weakens or reverses, halos might persist near eternally, anchoring the ashes of dead galaxies in a cold, dark cosmos. Some physicists speculate that in a heat-death universe, where entropy maxes out and all energy diffuses, halos could become the last structures standing, their gravitational wells acting as cosmic refrigerators in an otherwise uniform void. Stars will burn out, black holes will evaporate, but dark matter's indifference to thermodynamics might let it linger, a ghostly fossil of a vanished epoch. The wildest possibility, halos could transform. If dark matter particles decay or interact over incomprehensible timescales, they might morph into new forms of matter or energy, rewriting the rules of the late-game universe. Imagine a future where halos glow faintly with the fallout of slow particle decay, or where their gravity seeds new, alien structures in a rebounding cosmos. The true fate of halos isn't just about dark matter. It's a referendum on the universe's governing forces. Every observation of distant galaxy clusters, every simulation of cosmic expansion, brings us closer to forecasting whether darkness will outlast light itself. One thing's certain, in the end game of the cosmos, halos won't go quietly. They'll write their finale in gravity's last, fading whispers. What if dark matter halos aren't made of anything at all? That's the radical question at the heart of modified Newtonian dynamics, or MUND, a theory that dares to rewrite the rules of gravity itself. For decades, the existence of halos has been astronomy's best evidence for dark matter, their gravitational pull explaining why galaxies rotate too fast and clusters bend light too sharply. But MUND proposes a different solution. Maybe we've misunderstood gravity on cosmic scales, and these phantom halos are just an illusion born from our stubborn insistence on Newton's and Einstein's laws. The idea isn't as far-fetched as it sounds. When astronomers observe galaxies, they often find that stars at the outskirts orbit just as quickly as those near the center, a violation of Newtonian physics unless invisible mass is propping them up. MUND twist, instead of invoking dark matter, It suggests gravity weakens less sharply over large distances than current theories predict. Imagine a car accelerating downhill not because of hidden weights, but because the slope itself changes shape when you're not looking. For certain galaxies, especially isolated ones with delicate rotation curves, MUN predictions match observations eerily well, no dark matter required. But the cracks show when you zoom out. Galaxy clusters like the Bullet cluster present an existential problem for MUN. When two clusters collide, their visible gas slams together and stalls, while their gravity, measured by lensing, keeps moving ahead, perfectly aligned with the presumed dark matter halos. No tweak to gravity can explain this separation. You'd need some form of invisible mass to carry the gravitational signature independently. MUN proponents have scrambled to adjust, proposing speculative additions like hidden hot gas or neutrinos with improbable masses, but these fixes often feel like grafting dark matter through the back door. Then there's the cosmic microwave background, the afterglow of the Big Bang. Its speckled pattern encodes the early universe's density fluctuations, and the standard dark matter model nails these predictions with uncanny precision. MUN struggles to replicate them without ad hoc adjustments, leaving critics to wonder, if gravity is the issue, why does dark matter explain so much else so neatly? Even galaxies themselves aren't unanimous. While some spirals fit MUN expectations, others, particularly dwarfs with diffuse star distributions, still demand extra mass to make sense. This isn't just academic trench warfare. If MUN were right, it would upend physics, revealing gravity as a chameleon force that changes its behavior based on scale. Yet the weight of evidence, from colliding clusters to the large-scale structure of the universe, leans heavily toward dark matter's reality. That hasn't stopped MUN from evolving. Recent relativistic extensions like tensor vector scalar gravity attempt to reconcile it with Einstein's framework, but they're mathematically baroque compared to dark matter's elegant simplicity. Perhaps the most telling verdict comes from nature itself. Dark matter halos aren't just theoretical, they leave fingerprints in stellar streams, galaxy mergers, and even the peculiar motions of hypervelocity stars. Until MUN can account for these phenomena without resorting to invisible matter in all but name, it remains a fascinating but flawed alternative. Yet the debate is far from wasted. By challenging dark matter's dominance, MUN forces physicists to test their assumptions, refine their models, and stay honest. After all, the universe owes us no obligation to be simple or to conform to our favorite theories. The halos may yet hold surprises no one has dreamed of. From the ghostly fingerprints of dark matter halos bending light around empty space, to the cosmic dance of invisible giants shaping galaxies in ways we never predicted, we've journeyed through 25 of the universe's most tantalizing enigmas. Yet here's the humbling truth: every answer we've uncovered only peels back another layer of questions. Why do some halos defy their expected shapes while others vanish at their cores? What invisible currents of dark matter rain down on galaxies even now, unseen yet undeniable? And could these halos hold secrets about the birth of life itself, or the universe's ultimate fate? The beauty of these mysteries isn't just in their complexity, it's in their invitation to stay curious. Right now, telescopes buried deep underground are listening for the faintest whispers of dark matter particles. Supercomputers simulate halos with trillion-particle precision, searching for cracks in our theories. And somewhere out there, a future observation, a single anomaly in a galaxy's spin, a flicker of unexpected gamma rays, might rewrite everything we thought we knew. This story isn't finished. It's being written in real time with each of us as witnesses. Maybe your favorite mystery is the phantom rotation of halos, or the way they might hide parallel universes in their gravitational folds. Whatever captivates you, share it below, because the next great cosmic revelation could start with a conversation, a question, or someone like you looking up at the night sky and wondering, what else is out there waiting to be seen? The universe's greatest puzzles aren't just for scientists in labs. They're for anyone who's ever felt that thrill of the unknown. So keep asking, keep exploring, and remember, the darkest corners of space aren't empty. They're full of possibilities.